Welcome to homework.
Hello everyone, today we're doing chapter 23, problem 16, and this problem asks us what product is going to be formed when we first treat each of these starting materials with LDA and TFA, THF, tetrahydrofuran, at low temps. So we'll just say low temps. And then secondly, after that, we'll add this electrophile being this alkyl halide here. So what do we know about LDA, THF, and when we reacted in low temperatures? Well, let's look at A. So what we have here is this ketone, and this ketone has two alpha carbons, these carbons directly adjacent to it, and these alpha carbons have alpha protons. So what do we know about LDA and THF? Well, THF is just a solvent, doesn't really do anything. LDA, however, is a big, bulky, strong base. So at low temperatures, LDA, being big and bulky, is only able to fit on the side of the molecule that is least sterically hindered to rip off one of these acidic protons. So it being a base is going to act to be a proton acceptor or electron donor. So it's going to accept the proton from one of these acidic protons to form a conjugate base of this molecule. So if you see here, both of these alpha carbons are secondary carbons, so they're equivalent. So it doesn't really matter which one we deprotonate, but we're going to just deprotonate one of these alpha protons to get a carbanion. And now what we have is now a very strong nucleophile, this specifically a negatively charged carbon, which is highly reactive and highly unstable. So what it's going to do is want to pick up something to get four bonds and to satisfy the octet rule to neutralize itself. So in the second step, we're reacting that with an electrophile. So clearly what we can see is that there's going to be some sort of SN2 mechanism to make a new sigma bond. When we make a bond, we're going to break this bond, being with one of the halides, which is a very good leaving group. Now we're going to add those extra two carbons on our alpha carbon of the original molecule to yield the final product. And using the same logic, we can see that this alpha carbon is going to be deprotonated to act as a nucleophile, and then we'll pick up the electrophile. This carbon, and for this first molecule here, we see that nothing's going to happen on the left side because there's no protons for LDA to take off. So it's only going to be this right side. Similarly, for C, on the right side, there's an oxygen. Oxygen doesn't have any protons to be ripped off. So only this left side has an alpha proton that can be ripped off by LDA to form this nucleophile, which can react with electrophile to give us a product. And same with this cyano group. So alpha to the cyano group, the cyano is the same thing as a keto group. So it's a very electron withdrawing, and through both electron withdrawing effect as well as through resonance, it makes the alpha carbon and alpha protons highly acidic. So it's going to be this carbon here, so this proton. So let's start with B. So in B, we see that we're going to get deprotonation to form, in step 1, to form an enolate, which is a conjugate base due to the hydrogen withdrawing or hydrogen abstraction from LDA to get a very strong nucleophile. Then we're going to react it with 2 to get those extra carbons. So we're making a new carbon-carbon bond off the alpha carbon. Adding those 2 carbons. And C is going to be the same thing. After step 1, we have a very strong nucleophile. Then in step 2, it's going to react with that electrophile to gain extra carbon-carbon bonds. And a final product. And lastly, D. We get that carbanion that's going to react in 2 with electrophile to now get those 2 extra carbons.